Precalc Chapter 7, Sections 7 and 8. We're going to try to get through these pretty quick. So our goal today is to find the determinants. So 7.7 is how to find the determinants, and 7.8 we're going to use the determinants for a few different applications. So the determinant is a real number associated with a square matrix. It's only for a square matrix. The 2 by 2, you should be doing this by hand. It's pretty quick to do by hand. So if you're given the determinant where we have A1, B1, A2, B2, so the A's are the columns, the 1s are the rows, and 2's are a row. And so the determinant, DETA, or you can use the vertical lines, like it looks like the absolute value. So good kind of lesson for math is that we use the same symbols for absolute value as we do determinant. You have to realize what's the situation we're talking about. Since we're talking about matrices, we know we're talking about determinant. And so if we're having the vertical lines around the matrix instead of the brackets, we're using just straight vertical lines around it, then we know we're finding the determinant of this. To find the determinant, it's that downward diagonal multiplied A1 times B2 minus the upward diagonal. So the upward multiplied A2 times B1, and that's the process. It's the same thing as the denominator of the scalar when we were finding the inverse the other day. So let's find the determinant here of A. So A would be the downward, which is -3, minus the upward. The upward is 0. So the determinant of A is equal to -3. For B, the determinant of B is going to be -2 minus 0, so that's going to be -2. And so the determinant of B is -2. And we have to find the determinant of A times B. So we first need to multiply these. So we're going to do row times column. That's going to be -2 plus 0, -2. And then row times second column, so that's going to be 0 plus 0. And then row times column, and we get again 0. And then row times second column, and we get -3. And so we want to find the determinant of this matrix, and so we're going to get 6 minus 0, which is 6. So you can look at how the determinant of A and the determinant of B, if we multiply those, we also get the same thing as the determinant of A times B. Okay, 3 by 3. Finding the determinants of 3 by 3 is a little more difficult because we're still doing downwards minus upwards, but the issue here is that we have this downward diagonal here, but we also have another downward diagonal here, and then another one that starts up here. So we got to be careful with this. So our diagonals always start from these numbers. And so to help us realize where this diagonal is going here, let's repeat. We usually rewrite the first column, and then rewrite the second column. So now when we look at our downward diagonals, downward diagonal here, downward diagonal here, and downward diagonal here, we can see all the numbers. So we multiply them, so that's -6 times 3, so -18. We're going to add each of these downward diagonals. So that's going to be plus -2, plus 40, -80. So that's just the downward diagonals. Then we got to do the same thing for the upward diagonals. So 1, 3, 5, -2, 2, 2, and then 3, 8, -1. If you can see that within the same matrix without rewriting the columns, like how they kind of wrap around, then you can use that. But let's write the upward diagonals. So 1, -3, and 5, so that's -15, plus the next upward diagonal, -2, 2, and 2, which is -8. And then 3, 8, and -1, which is -24. So then you have to add up each of those diagonals. And so the downward diagonal here, we're getting -100. And then we're going to subtract the upward diagonal here, which is -47. So then we actually subtract the 2, so it's really -100 plus 47, so we get -53 is the determinant for A. So that's how you find it for a 3 by 3. For this one here, it's kind of a special case. We don't see it too often, but a triangular matrices, is when all entries on one side of the downward diagonal of a square matrix are zeros. So notice how these are all zeros. Whenever that occurs, all you have to do to find the determinant is multiply the downward diagonal. So to find the determinant of this matrix, we just need to multiply these three numbers together. So we're going to get negative 12. So that makes the process a whole lot easier for 3x3s if you have that triangular matrix. So here's another one dealing with variables. So you can see how we can have some of these where you have to know how to do this by hand without using a calculator. So if we're actually finding the determinant of this matrix, the downward diagonal is x times x, or x squared, minus the upward diagonal 2. That has to equal the other side 2. So now we create an equation here we need to solve. So add 2, so x squared is 4. Square root both sides, so x has to equal plus or minus 2. So that's it for 7-7. So let's look at 7-8. 7-8 is using the determinant to find the area of triangles, to look at collinear points, and then Kramer's rule, which is what we use to actually solve systems. Here's area of a triangle with vertices. So if you're given vertices x1, y1, x2, y2, x3, y3. So these are your 3 points of your triangle. The area can be found if you find the determinant. It's the determinant of this matrix. These should be vertical lines, not brackets. The determinant of this matrix times positive or negative 1/2. So notice how we have the x1, y1, 1, x2, y2, 1, x3, y3, 1. And so we have to have this row, right? We have to have this column of ones. This column of ones to make it a square matrix. We have to find, we can only find determinants of the square matrix. We include those column of ones to make it a square matrix. The plus or minus is just to make the area positive. Area has to have a positive value. Area is always positive. So choose the positive or negative. So when you multiply these two, you get a positive result. So example here, here's our x, y values for the vertices of a triangle. And so to find the area, it's going to be plus or minus 1/2 times the determinant of 0, 0, 1, 4, 1, 1, 2, 5, 1. So we have to first find the determinant. So that's going to be the downward, which is going to be 0 plus 0 plus 20, minus the upward, which is 2 plus 0 plus 0. And I can see that without having to write out the extra columns, because when I look at the downward diagonal here, this wraps to this number, this 1 wraps to those two numbers. So that's how I'm able to do that mentally. So this is going to be 20 minus 2, or 18. So then to find the area is going to be equal to plus or minus 1/2 times 18. And since 18 is positive, I'm going to use the positive 1/2. So it's just going to be 1/2 of 18, which is 9 units squared. So there's your area of that triangle. Test for collinear points. Let's first look at what collinear points are. Collinear points are on the same line. That's all it is. So these 3 points, if they're collinear, and you plug them into that same matrix and find the determinant of it, these are still vertical lines, so the determinant of that similar matrix we did the area, the determinant of that equals 0 means it's collinear. So collinear, if you found the determinant here and you get 0. So are these points collinear? If so, find the equation. So we got to plug them into the determinant, 3, negative 1, 1. We still have to add in this one column, so it's a square matrix. So we can find the determinant here. So that's going to be negative 9 plus negative 12 plus 0 minus the upward diagonal, which is going to be negative 36 plus 15 plus 0. So we get negative 21 and then negative 21. So then if I actually combine those, I get 0. Because this is 0, they are collinear. So these are collinear. Now we're not done because it says find the equation. So now we have to go through the same work back from Algebra 1. We need to find the equation. Well, this point right here helps it a lot because this is our y-intercept. So then we just need to find our slope. And we have an x change, so our m value, change in y or change in x. Our change in x is from 3 to 0 between those points, or 3. Then going from -3 up to -1 is a change of 2. So 2/3 is our slope. I'm looking at the rate at which those 2 points are changing, from 0 to 3 and -3 to 1. If you want to do the y2 minus y1 or x2 minus x1, you can do that as well. And so then we plug that into our equation. Y equals 2/3 x minus 3, and that would be the equation you get. Last concept is Kramer's rule, and it's for all square matrices. We can use this to solve a system. So really we're looking at this system right here. We have ax plus by equals e, cx plus dy equals f. We can solve for this variable by taking the determinant of EBFD. Now where in the world are these coming from? The denominator is what we want to first look at. This is the coefficient matrix. So the A, B, C, D is this coefficient matrix. The numerator has the same y column. So we look at this, the BD, these are for y's, and then we have these A and C are for the x. These are kind of the columns. So you notice how these x values that were A, C have been replaced with the solutions or the constants. So if we're going to solve for x, we're going to replace the x column in the coefficient matrix with the solutions, and that's your new numerator to find the determinant of. If you're doing that for y, we're going to take the y values, the y column, which is BD, so we have the BD here, and we're going to replace those with the EF. So we're going to take EF and put them in the Y column. And so that's how you set up for Kramer's rule. And then you just evaluate. You find the determinant of both, and you divide, and then that's going to be your Y value. So it's not too bad. The thing that really stinks about it is that you have to do one of these for every single variable you want to solve. So what I tend to do on quizzes and tests to help out for time is just ask you to find one of them. So I may ask you to solve for just y or just z in the problem to save some time, but still having you show me that you know how to use Kramer's rule. So Kramer's rule here. Let's just find z. Actually, maybe we'll find two of them. Let's start by finding z. To find z, we have to first find the coefficient matrix. So on the bottom here, it's just our coefficients: 4, -1, 1, 2, 2, 3, and 5, -2, 6. The numerator, I'm trying to solve for z. So this is the z column right here. So everything else is going to stay the same. We have 4, 2, and 5, -1, 2, and -2. Now this column, we're going to replace this column with these three numbers. Those three numbers go in place. So I'm going to put in the -5, the 10, and the 1. Then we have to find the determinant of both of these. So if we do that, our determinants are, denominator's determinant is 55 if you evaluated that. You can just punch in the calculator for the 3×3. And then the numerator has a determinant of 110. 110. So if we divide that, we find a z value of 2. So then we know z is 2. So it's not too bad for 1, but to do that for x, y, and z, then it gets to be a bit much. So we can do that for y, do it for one more here. The denominator still stays 4, 2, and 5, -1, 2, -2, and 1, 3, 6. Again, this is our coefficient matrix. Our numerator, since we're trying to find our y column is the middle one, the x column is staying the same, and the z column is staying the same. And we're going to replace the y column with our solutions, the -5, 10, and 1. That we have right here goes in. And again, we can divide that. We can find them using the calculator. The denominator is not changed. It's still 55. If you find the determinant for the numerator, you get 165. And so then if you divide that, you get 3. So that is Kramer's rule. So that is 7/8. We'll call it good. See you tomorrow.